Now next, say we wanted to find a 95% confidence interval for pi x minus pi y, or you can say px minus py. And the general formula is estimate plus or minus h. H is margin of error. Okay, so it's x bar minus y bar plus or minus z star times what? Times variance of x bar minus y bar. And further derive, this is x bar minus y bar plus or minus 95% confidence level. Z star is 1.96. And inside, just like what you see in chapter 7, it becomes variance x squared over nx plus variance y squared over ny. Are you with me? But for Bernoulli random variable, variance of x is pi x minus times 1 minus pi x. Variance y is pi y times 1 minus pi y. Okay? And x bar minus y bar, what we observe is from flipping the Looney 100 times, we see 50 heads. And flipping the tuning 50 times, we find 20 heads. Okay? So x bar minus y bar is what? 0.5 minus, this is 0.4. Am I correct? 20 over 50 is 0.4. Plus or minus 1.96. Here, you don't use what? Pi x or pi y to estimate pi x, pi y. You replace pi x by 50 over 100. Pi y is estimated by 20 over 50. So this is 0.5, this is 0.4. You plug in 0.5 here, you plug in 0.4 here. Is that clear? After you plug in the numbers, it becomes 0.5 minus 0.4 plus or minus 1.96 square root of 0.5 times 0.5 over 100 plus 0.4 times what? 0.6 over 50. And the whole thing you take square root. Okay? So a 95% confidence interval for pi x minus pi y is what? Is from minus 0.0674 to 0.2674. And take a close look. This interval do cover what? This interval does cover what? 0. And this interval is constructed from pi x minus pi y. So the data kind of support what? Huh? No difference in getting heads from what? The Looney and tuning. Is that okay? The probability of getting heads in tuning and for what? For Looney. Right? It's about the same. Can you see that? Because this interval covers 0.